Hi class, so now we're going to expand on conversions. So this is chapter 6.5. So chemical formulas as conversion factors, we look at a 3-leaf clover analogy. How many leaves are on 14 clovers? So if there's 3 leaves on 1 clover, then we can use that as a conversion, which is what we've sort of been doing this whole time, well, what we have been doing. But we're going to elaborate more on it and get into more detail now. So we have 14 clovers. Knowing that there's 3 leaves on 1 clover, we can use that conversion to determine there are 42 leaves from 14 clovers. We're going to use this. So let's go on and expand and try to use it with chemistry now. The formula for carbon dioxide, CO2, it means that there are 2 oxygen atoms per 1 CO2 molecule. So when we write this out, we can use these ratios of 2 oxygen atoms per 1 CO2 molecule. We can also use 1 C atom for a CO2 molecule. So we can pull out either atom out of this molecule and use it. So similarly, if we multiply this out, we can say 2 dozen oxygen atoms equals 1 dozen of CO2 molecules. As long as you keep the ratio what it is equal to, which is 2 oxygen atoms for 1 molecule, you can use a dozen, which I don't really feel is a good analogy, but let's jump to moles. This means that you have 2 moles of oxygen for 1 mole of CO2. It takes 2 moles of oxygen in order to make 1 mole of CO2 with 2 oxygens in it. I think that's a better analogy. So let's expand. You have a spider. 1 spider has 8 legs, and if you needed to use that as a conversion, you could. 1 chair has 4 legs, and 1 molecule has 2 hydrogen atoms in it. So inside this molecule, we have 2 hydrogen atoms, and we can also use that as a conversion factor, which is what we're eventually going to do. Okay, so formulas used in equations can represent units of individual chemical entities, or moles. So a chemical formula can represent an atom, an ion, a molecule, or formula unit. So we can use a chemical formula to expand and take so much information, more than you realize. So if we look at a 1H2O molecule, this means that you have 2 H atoms and you have 1 oxygen atom. That's a ratio. This means you have 1 molecule of water. You also have 1 mole of water. You have 6.022 times 10 to 23 molecules of water, and you have a mass of 18.02 grams of water for 1 mole. So this one chemical formula can give you a lot of information, and these are all equivalent. So this is where it needs to understand the connections, and sometimes this is where students have a hard time connecting when they're trying to do conversions, that yes, you can use some of these conversions because they're equivalent. Okay, so let's do a problem. Converting, find the number of moles of oxygen. So now we only want to know how many moles of oxygen are in 1.7 mole of calcium carbonate. So we have 3 oxygens in 1 mole of calcium carbonate, but we have 1.7 mole of this compound. So we're going to need to expand on this. So we have moles of calcium carbonate, but we want a mole of oxygen. So we need to look actually at the compound. So this is very similar to 1 chair has 4 legs. This is what we're doing. We take 1 mole of the compound itself and pull out 3 moles of oxygen because there's 3 oxygens in the compound. That's like saying 1 chair has 4 legs. That's exactly what we're doing. Now we can determine how many moles of oxygen we need or want. So we start with 1.7 moles. We use the compound of 1 mole for that compound and 3 moles of oxygen. And that gives us 5.1 moles of oxygen. Okay, so let's expand again. Find the mass of sodium in 15 grams of sodium chloride. So we start out with the mass. So this is a little bit more complicated because we're going to have to do more steps. We start out with mass, but we need to get to moles. We never use grams to determine what we have in that compound. It has to be in moles. Moles are the only thing that are equivalent for the 6.022 times 10 to 23. So we have to get it back into moles. Then we have to go to moles of sodium. Then we can get it back into grams because you just can't take it out. It will never work. So in this case, we need a lot of conversion factors. We need the molar mass of sodium chloride. We need the ratio of sodium to the sodium chloride compound, which likely for this one is 1 to 1. And then we need the molar mass of sodium. So we have that. So now we can start with 15 grams and we can just use all the conversion factors. And if we do it right, then the units will only end with grams of sodium, which is what we want. And we take a look, 15 grams, excuse me, and we use the molar mass, cancels out the grams of sodium chloride, we get to moles. We can use the ratio of the moles, and then we can use the molar mass of sodium, and that gets us to 5.9 grams of sodium, which is what we wanted. And it's 2 sig figs. So this worked. Okay, so the relationship is inherent in a chemical formula, allow us to convert between moles of the compound and moles of the constituent element and vice versa. What this means is that we can use the compound and we can pull out any information from that. So with 1 mole of carbon, tetrachloride, we also have 4 moles of chloride in it. We also have 1 mole of carbon for the same compound. So you can use it for whatever it is that you need to use it for. You just got to make sure that you understand the equalities. And in this case, 1 mole of carbon tetrachloride equals 4 moles of chloride, or it also equals 1 mole of carbon, because we have 1 mole of carbon in this. Okay, so we have a compound that's made of 10 carbons, 14 hydrogens, and 1 oxygen. And it is the main component in spearmint oil. It has a pleasant aroma and mint flavor. It's added to chewing gum, liqueurs, soup, soaps, and perfumes. We want to calculate the mass of carbon in this sample of 55.4 grams. So we start with 55.4 grams. So we need to figure out what we need for this to work. We need to go from, it's very similar to the last one. We need to go from grams of the compound, get out of the grams, always get to moles. Then we get to moles of the compound. Then we're going to determine the moles of carbon itself. And then we're going to use grams of carbon to determine how much grams makes up from this sample. So, oh, this moved on me, but it's okay. You need the color of the box more than what you need to see on top. So we're going to start with grams of carbon, which is 5.54 grams, and we're going to go to moles of the compound. But we use the molar mass in order to do that, so you have to add up all of those together, which I did in this box. You can see where the molar mass came from. Then we go from moles of the compound, and we go from that. If you notice, there are 10 carbons in this, so you have to account for those 10 carbons. So for 1 carbon, there's 10 moles. Remember, this is 1 chair, 4 legs. It may look weird, and it may not feel right, but that's exactly, you have to take the information from there. We have to account for those 10 carbons. And then when we get to that, once we get to the moles of carbon, we can use the molar mass of carbon. So let's use that. So we have 5.54 grams, and then with the 5.54 grams, we use the molar mass. That cancels out the mass, gets us to moles. Now we're in mass of the compound. We want to get to moles of carbon, which we do. And now when we get to moles of carbon, we can use the molar mass of carbon, and this gives us 44.3 grams of carbon. So what did I do here? That seems 55. I screwed up. So 55.4 grams is what it started with. So I think I put this down as 5.54, but this is 55.4 because this cannot equal more than this. So I calculated it with this being 55.4. So please make a note that this is not right. It's correct on the first slide, 55.4 grams. I always find things after I've run through them. So 44.3 grams of carbon is made up out of this 54.5 grams of the sample. But hopefully, even with that mistake, you guys see what I'm trying to say. And that's it.